Okay, welcome back. Hopefully you had a chance to think about that clicker question. Just in case you didn't, here's a reminder of what it was. Okay, so let's think about what's going on here, right? So we gave you the pattern of electron hits, and I think you might be able to sketch the probability density corresponding to that, and it would look something like this. So, prob. Namely, so plot our probability density psi modulus squared versus x, and this is at some fixed instant of time, so I could probably drop the t here. It would look something like this, right? We have nothing in the middle, and then two bumps where sort of on the sides. And you can see, I think, that right either of the two choices, A or B, if we square it, is going to give us something that give us a probability density that looks like this. So it is indeed the case that either one of the two choices given could give you that probability density. Good. Let's now do another exercise with wave functions, and I'd like you to think about the meaning of a wave function in this first whiteboard exercise. Now, in this whiteboard exercise, we've plotted the wave function, and the slide has just lowercase psi, which is usually the wave function at thinking only about the spatial dependence. So it looks something like this. So let's see here. So I'll make some tick marks. All right, and what you should hopefully get is that when you square this, you get something that's got a big spike at x equals -1. It drops to 0 at 0. And then we have the smaller bump over at 2, and then dropping back down. Right. So something like that. And then where is this particle going to be most likely to be found? Well, we've got the most. Oops, I forgot to label this axis. Right. Now the particle has sort of the most probability density right around here. So near x equals -1, and least likely to be found right where the probability density is 0. So at x equals 0, or for x greater than 4, or x less than -2. Okay, very good. So let's do one more exercise about wave functions and probability, and then we'll So let's have you think about that, and then we'll come back together. Okay, so the first part of this asks you to find the probability of detecting this particle between x equals -3 and x equals -1 millimeters. Well, that probability is going to just be given by the integral of our probability density between -3 millimeters and -1 millimeters. Right. But looking at this graph, right, that integral is none other than the area under the graph over here. So if I shade this green area in, right, it's simply the area of this triangle. So that turns out to be 1/2 times my base times my height. So that's 1/2. The base from -3 to -1 is 2 millimeters. And the height of my triangle is sort of one of these ticks, which is 0.25 inverse millimeters. And so if I do the arithmetic, this probability is 1/4 or 0.25 for finding the particle between -1 and -3 millimeters. Now, the sort of bonus part of this exercise asks you to calculate the probability of finding the particle within a really narrow 0.01 millimeter wide strip centered around x equals 2 millimeters. Now, this is sort of a question that asks for sort of a little bit of a trick. So think of it as the following. If I zoom in really, really close to x equals 2, so if I just stick my nose up here, right, I can maybe convince myself that the function is nearly going to be flat near x equals 2. Right, so for part B, right, so that probability is still going to be the integral, right, of my wave function, my probability density, so around x equals 2 millimeters. But now, right, so if I think about zooming in here, I can essentially approximate this as a constant. And you know, right, that if you think about an integral as a Riemann sum, right, I can essentially get away with approximating it as follows. So this is approximately equal to psi of x equals 2 millimeters. Delta x. So I'll change the d to a delta, because we're dealing now with a finite interval. So I'm just approximating this interval by pretending the probability density is approximately constant. And so this is going to just give me a value of 0.25 millimeter inverse, and my width of interval, delta x, is 0.01 millimeters. And if I go and do that, that's going to give me, so 2.5 times 10 to the minus 3. So this is sort of a handy dandy little trick if you're trying to calculate probabilities in some really tiny window where the wave function is not changing very much over that interval. Okay, so to wrap up today's class, I just want to mention two more things. So next time we'll say more about probability and how to calculate physically meaningful things given the wave function. But before we go, as a little bit of a bonus, I'd like to spend a moment talking about where the wave function comes from. Now, classically, right, you can find the displacement for a wave by solving the wave equation. And the classical wave equation, as you'll remember from the last homework set, looks something like this. It's a partial differential equation. So it goes like d squared, the displacement, partial x squared equals 1 over, and I'll just use v now for the wave speed, v squared, d squared, dt squared. Now, for a given physical situation, like a wave on a one-dimensional string, you can usually derive the wave equation from some more fundamental principles. I think it's in Knight how if you write down f equals ma, you can get the wave equation out. You can maybe even sort of see the hints of this, right? The acceleration in the turns into this second partial derivative with respect to time, and then f net ends up coming from curvature of the string, which gives you this second derivative, a second spatial derivative term here. If anybody's sort of dying to see how that goes, I'd be happy to make another video where I work out the wave equation for say like a 1D string. So quantum mechanically, so you get the wave function comes from solving the Schrodinger equation, which is also a part of partial differential equation, and it happens to look like this. Minus h bar squared over 2m d squared psi dx squared plus some potential energy that varies in space possibly, and this all equals by h bar. This time it's just a first derivative, partial psi, partial t. A few bits of commentary here, and we'll have much more to say about this going forward. H bar is simply Planck's constant divided by 2 pi, and just turns out to be more convenient for lots of things, as we'll see as we go on in the course. Here, m is the particle mass. And what else? Oh yes, I should explain this is the potential energy. And we'll have more to say about that later on. But I just wanted to mention as sort of the difference between classical and quantum and what we're going to do. So I'm going to guess that in Physics 217 you weren't spending tons of time solving the classical wave equation under different conditions, etc. You just you were taking solutions to the classical wave equation, like a sinusoidal wave, and then thinking about what those solutions imply. We're going to take the same approach with the Schrodinger equation. We're not going to start off by trying to solve it in different potential energies, even though we will do that starting in chapter 3. In this chapter of Townsend, we're going to think about what the solutions mean physically, but then starting in chapter 3, we will start to solve the Schrodinger equation. Now, the one thing I should say is that unlike the classical wave equation, where like I can point to F equals ma and write this down for a wave on a string, I can't derive the Schrodinger equation from anything more fundamental. This is a new physical idea. Just like for Isaac Newton, introducing F equals ma was a new physical idea. For Erwin Schrodinger, this equation is new physics. Now, he didn't just pull it out of thin air. Ultimately, Schrodinger comes up with his equation by using it to explain the spectrum of hydrogen. Now that's a really rich and fun problem. We'll say a little bit more about hydrogen and atoms towards the end of the course. If you take advanced quantum mechanics, physics 421, you might actually do the solution to the Schrodinger equation for hydrogen in detail. We'll probably look at it in this course, but not go through all the gory steps involved. But that's sort of where his motivation came from. But if you feel like this equation just dropped out of the sky, you're right, because I really did just pull it out of thin air, and we could try to come up with some sort of plausibility arguments, but they're not really satisfying, in my opinion. And I think we just have to try to take this as a statement of what nature does, just like we take F equals ma as something that's consistent with experiments, but that describes how nature behaves. Alright, so that's it for today. Thank you very much. Please send me any comments or questions that you have, and then we'll see you next time.